Hello friends, today we will learn the conformations of the disubstituted cycloalkane. So this is the before going this disubstituted cycloalkane. First let us see this chair form of the cyclohexane that we have seen in previous lectures also. So in this you can see there are the three hydrogen in up position. You can see this is the hydrogen up the 1, 2, 3 and 3 are in down positions. So 1, 2, 3 are in down positions. And these are called as the axial. You can see this is the equatorial hydrogen. So there are 6 hydrogens are there. So I have compiled all these up and down hydrogen in a table. You can see here this is a position. So if you take position like 1, 2, 3, 4, 5 and 6. Okay. So 1, 2 or 1, 4. So if 1, 2 or 1, 4 is A, E or EA. So if it is taking A means this is axial, this is E. This is called as the cis. A and E is called as the cis, not EE. If you take EE or AA, it is called as the trans. You have to remember this thing. If it is 1, 2 or 1, 4. 1, 2 or 1, 4. You can very easily remember. So both axial, both equatorial is trans. But if you are taking AE and EA, it will be cis. You have to remember 1, 2 and 1, 4 position. But when you will take 1, 3 position, 1, 2 and 3, 1, 3 position, this is the 1, this is 3. In this case, if you take 2 axial, will be cis or 2 equatorial will be your cis. So 2 axial or equatorial, whatever you will take, it will be cis. And trans means again, it will be opposite of 1, 2 and 1, 4. So if you are taking A and E or E or A, so it will be your trans. So you have to remember this formula because only this table will help you in solving the many problems. So you have to remember this one. If you take a 1, 2 or 1, 4, double A will be trans or AE, EA will be cis. Opposite of 1, 3 will be this one. So if you take opposite of this one, this becomes your 1, 3 position. So based on this table, we will learn the stability of the disubstituted cyclohexane. Cis isomer, what is the meaning of cis isomer? Two substituent on the same side, either both will be up or both will be down. That is called the cis. Like a double A 1, 3, or you can see AE 1, 2. So this is the your cis isomers, or both on down. Both on up means double A, both on down means 1, 3 position E. Similarly in trans isomers, so if you take, you have to, this will be the across the carbon. The two substituent on opposite side of the ring, one is up, one is down, is called as the trans isomers. Now let us see through this diagram. So this is cyclohexane, this is the one CS3 and one CS3. Though this CS3 is down, this CS3 up. So both are E position. And if you flip it means this carbon is going down and this is going up. So this is up. If you put up, so this will convert into A. So when you are flipping, E is converted to A and E is converted to E. So both are E, so both will convert to A. So this cyclohexane is less stable because this will interact with 2 hydrogen. So this is 1 hydrogen this side, 1 hydrogen this side. So again it is interacting with the 2 hydrogen. This is called gauge interactions. Again similarly, this axial will interact with 2 hydrogen, 1 hydrogen this side, 1 hydrogen this side. So the CS3 hydrogen interaction is there. So this is less stable, while CS3 there is no gauge interaction this side or this side because both are opposite. So this is more stable than that of this one. You can see a diagram I have drawn here. 1, 3 diaxial interaction. So steric hindrance is there, steric interaction is there. So this is cis 1, 4 dimethylcyclohexane, which is again creating the instability due to the more interactions. So again you can see it from this diagram, it is very clear. So this axial methyl interacting with this 2 hydrogen up and down, and similarly this is interacting with the hydrogen and CS3 1, 3. So again down interactions is there. So definitely this is more interaction, so this is again less stable, this will be more stable. Similarly you can see from this diagram which is more stable. So this is the cyclobutane. So in cyclobutane, this is the double O methyl. You can see here, this is the CO methyl ester is there. Then ester is, this is the E group, this E group, cis E1E 1,3 dimethyl carboxylate cyclobutane. This is the carboxyl cyclobutane. And this is the up and down, this is the trans 1E. So trans means there is 2 axial position, this is the cis 1E 2 equatorial positions. This is more stable because this is in equatorial position, this is in axial position. So this is your less stable. Let us see the dihexane interaction between the cyclohexane. So this is the 1,1 dimethylcyclohexane. So this can be written as the in chair form like this. If you flipping, so this will go down. So axial is this axial, this is equatorial. Axial convert to equatorial. This will convert into your axial. You can see this is going down. This is up. Is clear? Next you see 1 tertiary butyl 1 methyl cyclohexane. So in this you can see the same thing is happening over here. So this is in axial position. This is your equatorial position. So in this case, this is the bulky group. This is the less stable. This will be your more stable as compared to this one. So stability order, this is more stable, this is less stable. Why this is more stable? Because this whole bulky group is in axial equatorial position. So this position is equatorial, so this is more stable. This position is axial, this is your less stable because it is interacting with the hydrogen from this side, hydrogen from this side. So there is more gauge interactions in this case. Similarly, this is cis-1,2 dimethylcyclohexane. So this is 2 up is there. So this can be written in the form of like this also, like this also. So this is the form it's called. So this is the 1A, 2A is there. You can see it's very clear 1A, 2A, and there is one more conformation is 1E, 2A. So both are almost same size. Means it has only one conformer. So there is a like this one. So both is same. Here stability cannot be determined because both are same. But if you take in case of trans 1,2 dimethylcyclohexane, so one is down, one is up. But in this case, we can draw two your structures. So this is the two your you can say two equatorial there 1E 2E. In case this is the axial 1A and this is the 2E. So 1 2 you can say this is interacting with the 2 hydrogen. This is interacting with 2 hydrogen. So this is less stable. There is no interaction because both are in equatorial. So this is more stable. So trans 1 is more stable and trans 2 is this trans conformers of this is again second is more unstable because of there is two gauge interactions. You can see this CH3 interaction with the one hydrogen this side, one hydrogen this side, while this will interact with the one hydrogen this side, two axial interaction. So this is your less stable. Similarly, if you see 1,3 dimethylcyclohexane, in this case you can see the diagram. So both diagram is the 1,3 is there. So this is the 1E, 3E. So there is no interactions, but in this one axial, both are opposition. So there are two conformers in this case. So this is again less stable. This is again more stable because both are equatorial position, and this again less stable because this will interact with the one is methyl group and one with the hydrogen. So this side is hydrogen. So this will interact with this hydrogen. This also interact. There are three gauge interactions, or you can say steric interaction between CH3 CH3 and CH3 hydrogen CH3 hydrogen. So this is less stable and this is more stable. In trans 1,3 dimethylcyclohexane, so in this case what happens? This is the methyl, this methyl, one is up, one is down. So this is your up and this is your down. So this is it becomes your 1E 3A, the axial 1,3A. And similarly, if you flip it, so on flipping, this becomes your axial, this becomes your equatorial. So both are almost same structure. So in both the cases there is two diaxial interactions. So this is interacting with two hydrogen. Again this is interacting with the two hydrogen. This is equatorial. This will not interact at all. So only one is interacting. So there is one conformer in this case. Now if you draw this one cis-1,4 dimethylcyclohexane, this is again two opposition to up position. So in the chair form, right, one up, one up. So this is interacting with the two hydrogens. Similarly, if you flip it, this becomes your axial, this becomes your equatorial. So again, it has only one conformers. So again, interacting with the two CH3H. There is two 1,3 diaxial interaction. In this case also, there is one two diaxial interaction CH3 hydrogen. So only both are one conformers. Trans 1,4 dimethylcyclohexane, it will be two conformers. Let us see how. This is the diagram. So one is up, one is down. This is the one up, one down. 1E, 2E. Similarly, if you ring flip it on flipping, this will equatorial will convert to axial, and this equatorial is converted to again axial. So again, this is both up and down, both are up and down. So 1E, 2E, and 1A and 4A. So definitely this is more stable because there is no diaxial interaction. But in this case, CH3 is interacting with the again two hydrogen, one hydrogen this side, and again this is interacting with the, again two hydrogen. So there is a 4 into CH3 hydrogen. There is a 4 interaction. This becomes again highly unstable, or this will destabilize this chair form of this molecule, that is trans 1,4 dimethylcyclohexane. This is more stable because there is a both are in equatorial position. Both methyl are present in equatorial position. So let us see this picture form. This is the CH3 group, CH2 group. In the case of ethyl, this is the up position, this is the down position, and again in this case this is again axial position, this is axial position. Definitely this will be your less stable, because this will interact with 2 hydrogen, this will interact with 2 hydrogen, but in this case this will be your more stable, because there is no diaxial interaction with this ethyl group. So this is more stable conformational isomers for trans 1,2-diethylcyclohexane. So this is a one case, this is a bromine, this is a tertiary butyl. So this we can draw in this like, this is up, this is down. So this is the up position, this is the down position. So there is no diaxial interactions, but in this case if you put bromine up, this one up, both are in up position. So this bromine is again interacting with the 2 hydrogen here also. In this case this tertiary butyl will not interact, so only 2 hydrogen interacting with the bromine. So again this is your less stable as case of this one. And in this case this is the again board form of this molecule. So this is highly unstable, because this is giving a highly unstable, because both this is in the equatorial position, this is a bromine position. So there is a unstability in this molecule as compared to the chair conformers. So this is the cis 1, 2, 3, so all in up position. So we can write like this one. So this is all 3 in up position, and if you flip it, so on flipping this becomes your down, this becomes your axial converted to equatorial, and this is up. So this is more stable, because 2 are in axial, 2 are in equatorial. So this is again equatorial, this is equatorial, this is axial. Similarly in this case 3 up means this is equatorial, this is equatorial, up, this is up, again up, this is axial, up. And if your ring flips, on flipping, this flip up, this turn into axial, and this will turn into axial. So if you down, this will turn to axial, and this will turn to equatorial. So this is more stable, because there is a 2 equatorial and 1 axial. In this case there is a 2 axial and 1 equatorial. So there is a more 1,3 diaxial interaction over here. So this is again less stable. This is again less stable. This is again more stable in terms of energy. Now in this case all cis 1, 3, 5, so all 3 in up position. So these 3 are in up position. So again if you ring flip, this convert to equatorial, this will turn into again you can see this equatorial, this equatorial, and equatorial. So definitely there are 3 equatorial, so this is more stable, and there are 3 axial, this is again less stable, because there is a, again you can see diaxial interaction between these 3 CS3 groups. So this is definitely this is highly strain energy between these 3 methyl groups. So this is type 2 unstable, this is type 2 more stable in this compound. Determine the following compound is cis isomer or trans isomer. So already we have defined already what is cis isomer, what is trans isomer. So these are the 6 examples, A, B, C, D, E, and F. So I have given already. So this is 1, 3. So 1 E, 3 E. So when 1 E, 3 both E is there, this is called cis. When it is bromine is, again you can see it is in axial, while methyl is again axial, equatorial. So 1A, 4E is again 6. So 1, 4 is cis when A is there, or 1, 3 is double E is there, is called cis. So you have to remember this thing based on the previous table. Similarly, if you take C1, so this is your 1E and 3E. So 1E, 3, again it is cis. Cis is 1E, 3 is cis. Again in case of D, this is axial, this is again this is equatorial, this is axial. So 1E and again 3A, 1E, 3, this is called trans. If this is cis, this will be your trans. Similarly in case of E, both are in equatorial position, this is called as trans. In case of 1, 2, and in case of your 1, 4, both are in E is there, so this is called as trans. So both opposite or both same side is called trans. If anything will be opposite, like one axial, one equatorial, this will be your cis, or opposite, one will be axial, or one this is called cis. Remaining, if you take the opposite of this in 1, 3 diaxial positions, so it will be reverse of this value that we have seen in this case 1, 3, 1, 3, 1, 3. So EE or AA, it will be always cis, but if you take 1E, 3, it will be your trans. So you remember this is a table will be very helpful in understanding what is cis and trans positions. Draw the stable chair form, stable conformation of chair form. So you can see the 4 group is there: methyl, OH, Br, and tertiary butyl. So this is the, you can see there are 2 chair forms. So this is the 1, 2, 3, 4, 5, and 6. 1 is methyl up, because this is methyl in up position. OH is again down, so OH is again second carbon down position. And fourth is bromine. Bromine, you can see it is in again axial position down. Again tertiary butyl is down is there, so tertiary down means this is in at equatorial positions, because this is up, this is down. And if you flip it, on flipping what happens, we can also draw. So OH will come into axial to equatorial. This methyl is again, it will come into here axial to equatorial, and this will come into equatorial to your axial position. Okay, so in this case you can have 3 axial, 1 equatorial. In this is 3 equatorial, 1 axial. But since this is more bulky group, so this is more unstable, because it will be interacting with hydrogens over here. And this is more stable because this is your massive group in equatorial position, remaining 3 axial. So in this case, this is more stable cis form or chair form of this whole molecule rather than this form. Now we have one more molecule, CH3 in fluorine. This is form, and another is, this is the transform CH3F. Now in both the cases, which is more stable? Let us draw the diagram. So this is down, this is down. Down means again this will be your axial position, this will be equatorial position, and this is up and down. So up is, this comes on equatorial position, this will be your again equatorial. So this is a diagram. You can see cyclohexane, which having 2 chlorine and 1 methyl. This is 2 chlorine up position and 1 methyl down position. So if you draw the chair form, so this 2 is up. So 2 up means you can see here, this is the 1 methyl and 1 CS, 1 Cl is this side. So you just you write here, this is a CS3. I forget to write CS3, and 1 Cl is again up, so we can write in actual position, this equatorial position, and this methyl is down. And if you flip it, on flipping, this becomes your axial, becomes your equatorial, and this becomes your axial. So this is over here. Now if you just note down this 1,3 diaxial interaction, that is the energy wise. So this CH3 interacting with the 2 hydrogen, and again down CH3 interacting with the 2 hydrogen. So there will be total energy will be how much? So for CH3, 1 is 3.75 kilojoule per mole. For 4 CH3 hydrogen, so it will be 1, 2, 3 and 4. So if you multiply by 4, you will get this much joule, kilojoule per mole. In this case, this is equatorial, so there is no diaxial interaction, but Cl is interacting with the 2 hydrogen. So for 1 hydrogen, it is for 2 hydrogen, it is 2.2 kilojoule. Actually 2.2 kilojoule is the for 1 hydrogen, so it's not 2, and for this is nothing, total is 2.2, so it will be 2.2 kilojoule. So again, if you subtract 2.2 from here, if you subtracting 2.2, 15 minus 2, is the total is 15, 15 minus 2.2, so you will get after the something 12 point, it will be 12.8. So 12.8 by this much energy, this is more stable than that of this, and this is nothing but the free energy of this molecule, and it is more negative. So if you put this value, we can find the K equivalent also. Once we find the K equivalent, then we can calculate E and A that we have already seen in the problem sections. You can understand this numerical in the problem sections. So higher the K value, more is the stability of delta G. Now we'll see next one more numericals. Each methyl hydrogen 1,3 diaxial interaction is imparting this much kilojoule per mole, and while the methyl 1,3 diaxial interaction is imparting this much kilojoule per mole. Instability to a compound. This is giving this much instability. Find the energy difference between the more stable conformers of. So there are 3 examples. You have to find the energy difference between these 2 stable conformers. Cis trans 1,3 dimethyl cyclohexane, EEA trans 1,2 dimethyl cyclohexane, cis and trans 1,1,3,5 tetramethyl cyclohexane. So this is first one, cis and trans 1,3 dimethyl cyclohexane. So this is 2 in equatorial position, and this one is equatorial, and this is your axial position. Both are trans position. We have 2 conformers in this case. 1,3 dimethyl, we have 2 conformers. One is EE form, one is EF form. Now in which is more stable? So already we have seen there is no, we can see the diaxial interaction in this case. So this is cis form, and this trans form. You can see there is a 2 diaxial interaction, because this will not contribute in the diaxial interaction. So for this one, energy is 3.75, totally 7.5 kilojoule of energy is the instability, and this is no interaction there. Definitely this cis form is this much kilojoule per mole of more stable than that of trans 1,3 dimethyl cyclohexane. Now in second case, you can see this is the diagram. So this is a we have seen this is EE or A trans 1 to dimethylcyclohexane. This is the EE form, this is the AA form. So this is trans AA form, this is trans AA form. In this case, there is no interaction, both are in equatorial position, but in this case, both are axial position. So this methyl is interacting with the 2 hydrogen, this is a flagpole hydrogen. Again, this is interacting with the 2 hydrogen over here. So there will be energy will be total. So 4 into each interaction is 3.75. So multiply by 4, you will get 15 kilojoules. Definitely, this isomer is more stable by this much molecule, because this much energy will cause the instability of this molecule of chair form, and this is more stable by this much energy. So trans 1E 2E is more stable by trans 1A 3A by this much 15 kilojoule per mole. So this is the third case. See, cis trans 1135 tetramethylcyclohexane. So this is the 1, 1, 3 and 5 tetramethylcyclohexane. So if you see, calculate the diaxial interaction. So this methyl is interacting with the 2 hydrogen. These 2 are in equatorial, no interaction. Again 3 is also at the equatorial position, no interaction. So total energy will be 2 into 3.75. It will be 7.5 kilojoule per mole of strain energy. This is cis 1A, 1E, 3E, 5E. In this case, on flipping, this becomes your again axial, and others becomes your axial turn into equatorial, equatorial turns to axial. So you will get these structures. The trans 1A, 1E, 3E, 5A. Now you can calculate trans 1A, 1E, 3A, 5A. Now what is the strain energy? So this methyl interacting with the hydrogen methyl. So there is a 1 methyl interaction and 2 CH3 hydrogen interaction. These 2 are in equatorial, so there is no interaction. Total energy will be, for methyl it is given energy is 15 kilojoule per mole, but in case of CH3 hydrogen, there is 2 CH3 hydrogen, so total energy will be 2 into 3.75. So total energy is, if you calculate, 22.5 kilojoule per mole. Now this is how much? 7.5. This is 22.5. So definitely this form is how much more stable. So it is subtracting 22.5, 7.5 joule. So it becomes 15 kilojoule per mole. So this form is 15 kilojoule per mole is more stable than the trans form of this structure. So I hope you have understood this numerical carefully, how we can calculate the strain energy of this chair form by using this 1,3 diaxial interactions. So these are the energy value of different molecule like CH3 interacting with the hydrogen, 2 hydrogen. So this is total energy. So this is the axial strain. Similarly, CH3, CH2 interacting with the 2 hydrogen. So this much energy. Similarly, this is your isopropyl. So this is 2.2 for phenyl. CH5 2.9. Tertiary butyl 4.9 means 4900 calorie per mole. This is the highest. This is giving heavy this axial with the hydrogen. Similarly, different values given for fluorine this much, for bromine and chlorine you can see their interaction almost equal. For OH little much more, for NH2 1.4 and for carboxyl 1.4. So it is again, if you take this type molecules, again it is. So why this value is counted? This is you have to this value will be given while calculating the diaxial interaction in the formula. So already we have given before 2-3 examples. Let us see one more examples. So this is your you can see this is a phenylcyclohexane. So methyl phenylcyclohexane. So if you draw this in this form, this is your axial form. This is your again axial form, equatorial axial form. So this actual form is interacting with the 2 hydrogen, and this equatorial has no diaxial interaction. The total energy will be 1.7 kilocalorie per mole, because 2 into CH3 and hydrogen interaction. Now if you flip it, this convert into your axial position, and this will convert into your equatorial position. So in this case there is no interaction with this case, but this phenyl will interacting with the 2 hydrogen. In this case, what is the energy? 2.9 kilocalorie per mole from the your axial strain table. So this is 2.9, this is the 1.7. So definitely the phenyl equatorial. This is the phenyl equatorial is stable by how much kilojoule? 1.2 kilocalorie per mole. Now let us take one more case. This is the phenyl and this is the axial. So and again we know the calories total much how much. So this is an axial position and this is axial position. In this case, how we can calculate? So again 2 into CH3 hydrogen is 1.7 and phenyl is also interacting. So transform, so total energy will be 4.6 kilojoule per mole. And in this case both are in equatorial position. There is no diaxial interaction. So definitely out of these two, this will be more stable. This will be again more stable from this by 4.6 kilocalorie per mole. So now let us please try to solve this numerical by yourself. The actual conformation of the fluorocyclohexane is 1 kJ per mole, that is this much kilocalorie per mole, and this is less stable than the equatorial conformation. So what is the energy cost of a 1,3 diaxial interaction between the hydrogen and fluorine? Second question, bromine is larger than chlorine, but the two atoms having the identical axial destabilizer energy. And explain. So try this question by yourself. It is quite easy. Now let us see some special cases of cyclohexane. So this is the example of cyclohexane 1,3-diol. You can see this is the 1 carbon, 3 1,3-diol. This is down, this is down, and we can write this in the chair form. You can see both are 1e and 3e. Cis 1,3, this is cis form. Similarly, this can be written as this is the down form, this is the up form, this is up structures, and this is a trans form 1e and 3a. This is the 1e and this is the 3a, 1 3 up and down. Similarly, this is down, this is up. So you can see here 1 3a. So this is the up and this is the down for this one. There is a second example, cyclohexane 1,2-diol. In this case, you can see this up and down. So structure will be like this, up and down. Similarly, this up and down structure will be like this. This is up and down 1 2 structures. Cis 1,2 cyclohexane diol, both are up structures. So in this case, up structure. So this is axial and this is the E. Cis structures. So on ring flipping, this will convert into your up and down. You can see structure. So this is your E becomes your axial. This becomes your again equatorial positions. So this is 1e 2a. It's converting after ring flipping 1a and 2e. So this is 1,2 cyclohexane diol. In this cases, you can see this 1,3 structure in axial position. So they are forming the hydrogen bonding. So this chair form in 2,1,3 cyclohexane diol is more stable due to intramolecular hydrogen bonding. Again, you can see the structures. If you are putting this hydrogen in this side and this hydrogen in the opposite side, so both the structures are same. Again, you can see in 1,4 positions. In this case, also due to this intramolecular hydrogen bonding, this both structure is more stable than the chair conformations. Now we'll see some conformation of the fused rings. The fused rings means these rings are attached to each other. So this is the decalin structure. It is called as bicyclo 440 decane. So again, if you write in the cis form, these are cis forms, 2 hydrogen up and 1 hydrogen up and down. This is a transform, cis and transform. So if you draw the cis form in the chair form, you can see in the chair form also this structure will be cis forms in the form of chair. So on flipping, if you flip this ring, so this is your down, this is up. So the structure will goes like this or like this. There are 2 structures of cis decalin, 1 2 3. So on flipping you will get these structures. This is a transform of these structures, transform in chair form. But in this case, ring flip is not possible, because in this case, if you flip the ring, the carbon-carbon bond will break down. So ring flipping is not possible. This is the tricyclic structures of adamantane. So this is a chair form. So in this way, we can draw many structures, but all these structures are not in the syllabus, so we cannot go beyond that. This is the beyond the JEE syllabus. So again, tricyclic structures are this structure is there, so we cannot go much more. Let us see some examples. So let us see this structure, cis decalin. Already I have shown you this printed pictures. You can see very clearly. So ring flipping, it becomes these structures, and for trans decalin, it is not possible because it will lead to the breakage of CC bond. Now this is in the bond line structures of trans decalin, up and down. So under ring flipping, it will go like these structures. But it is not possible in this ring case, it will break down. But in cis decalin, if you draw, if your ring flipping occurs, so it will convert to this structure or this to this structures. There is one more diagram. So this is the decalin in cis structures in 2 forms, this and this form, and it is surrounded by the, you can see these are the 1 to 6 again chair forms, but these structures are the glucose structures in the chair form. Similarly, this is the transfer, this is cis decalin of another structures. So again, you can see the same structure of glucose in this position. So this is the asteroid conformers. this conformation of an asteroid, and you can see that structures is 4 chair forms are there. This is the cyclopentane and 3 are the cyclohexanes. You can see their trans structure of this chair form, and this is again you can see the cis forms of these 4 structures.